All right, so we're coming up on 5 minutes here, so we'll go ahead and get started. This is the ArangoDB meets NVIDIA Triton Inference Server workshop. Probably easier said, ArangoDB meets NVIDIA Triton. And this will be primarily led by myself and Sachin. And some of the first things that we wanted to point out is to get started, where we suggest cloning this repo, as it could be, there are some steps that can take a little while, and I will kind of let Sachin take over, but I did want to go ahead and paste in the repo link, and specifically, if you look in the repo, there's the README to download the NVIDIA Triton Server Docker image, which might just take a little while. So go ahead and get started now. And then by the time that we get to the hands-on portion, you should be ready to go with everything downloaded that you need. So yeah, again, just if you are planning on following along, start by downloading those. And we'll try and build in another reminder a bit later for those that come in a little while. But for now, yeah, definitely start here. And then, yeah, I think, Sachin, you wanted to start, and then we'll switch back to me in just a moment for a brief intro to ArangoDB.
Yep, thank you, Chris. I'll just quickly share my screen. So I guess like everyone can see my screen.
Yes, yeah, we can see it.
Okay, cool. So welcome everyone to our webinar / workshop on Arango database meets NVIDIA Triton Inference Server. With me joining is Christopher Woodward, who is a developer relational engineer at Arango database. So this is an interactive workshop, so feel free to raise any questions. This webinar includes an introduction study of Arango database and NVIDIA Triton Inference Server. In addition to this, we will also have an hands-on session where we will observe how both of these technologies can complement each other. Having said that, let's kick it off. So, okay, so Chris, I guess like I already have told you about the important downloads. Yeah, so this is the agenda for this workshop. First, we will have a brief description about Arango database, like what we are doing and all, and then we'll have an introduction study of NVIDIA's Triton Inference Server, about like what's the need of this server, what are its different features, and what are the different components or the architecture of the Triton server. Then we'll see like how the Arango database apply to Triton Inference Server. So this workshop is an introductory one. We're also planning to have the second workshop, which will be an advanced one, which will revolve around the concepts of graph machine learning, training your graph machine learning model, and then deploying the model, and then performing graph analytics over it. And so I will also show you the glimpse of like what's the second workshop looks like. And then afterwards, like we'll have our final round of hands-on experience. So this is me. I'm a graph machine learning researcher at ArangoDB. I have completed my master's in intelligence system at Technical University of Kaiserslautern. Before that, before joining ArangoDB, I was a former machine learning scientist and engineer at Define Media, where my role was to build machine learning pipelines, build machine learning algorithms, and deploying machine learning models to production. I was also as a research intern. I also worked at the German Research Center for AI. I also like to blog a lot, and you can see these some of my important the blog publications which I did on Medium in this second row. And yeah, my main interests are in computer vision, natural language processing, and graph machine learning. So, yep, handing over to you, Chris, now.
Alrighty. Oh, and I will second here. Okay. There we go. All right, let's get back to that. So yes, as you said, my name is Chris. I am the developer relations engineer here at ArangoDB. And you may have already seen me on various videos, things like that. I am heavily involved in working on the training and getting started with development at ArangoDB. I'm frequently reaching out to the community to try and find ways to make it easier to get started, or just find new and interesting ideas that maybe the community is already working on. And maybe just sort of a quick plug there as well for the Community Pioneer program. We're always happy to have members of the community showcasing projects they're working on. These can be personal projects. They don't need to be something you're working on for a company. Just anything that you think that might be interesting to the ArangoDB community of developers, or even if you just have a cool tool or utility that you might like to have help with from the community. We have the ArangoDB community org as well that we like to start putting more projects on. So if you have any interesting ideas you'd like to share, definitely feel free to reach out to me through either my Twitter, or probably best through the Slack community Slack channel. My official tag there is chris.arangodb. And so my part in today's workshop is going to be just doing a quick overview of ArangoDB, ArangoDB as a company, and then some of the technologies that help make ArangoDB as awesome as it is. This will be targeted more for people that aren't already familiar with ArangoDB, and will just be a really quick sort of glance at some of the features and things that make up ArangoDB. So not really a deep dive, but if you are interested after this, we have a ton of learning content available through our website, arangodb.com, as well as a free getting started Udemy course if you're more interested in like video courses like that. And all of that stuff can be found directly on our website at arangodb.com. Okay, and so ArangoDB is the first native beyond graph database. So what that kind of means is ArangoDB is a native multi-model database, and that was founded in Cologne initially and has headquarters in San Francisco. It is an open source project. We have an open source community edition as well as an enterprise edition. We are quickly growing. We are well, I think, over the 65 employee mark, with 11 million downloads, 600 product installations, and 12,000 stargazers on GitHub, which we are very proud of. And if you do end up thinking that you like ArangoDB, we'd love for you to star us on GitHub. And also, we are a leader on G2. And so any reviews you leave us on G2 are always greatly appreciated as well. And so I mentioned that ArangoDB is a native multi-model database, and this sort of is a full picture, or a good picture, of everything that comes with ArangoDB. And we kind of like to think that we start from the graph out, so the graph and beyond. As you get access to a graph database and without any compromise. So you also have access to a full document store, key value store, as well as a built-in full text search engine. and then graph analytics and machine learning from there. So we do have Pregel built in, and currently experimental custom Pregel feature. We also have a full suite of tools with graph ML and analytics with our ArangoML tool suite. And we also have a Kubernetes integration that is actually the backbone for our managed service Oasis. This is our cloud managed service. Actually has a free trial as well if you're interested in ArangoDB in the cloud. Definitely be sure to check that out, cloud.arangodb.com. And the like big takeaway, and the reason I've sort of mentioned this native multi-model thing multiple times, is that all of this is inside of a unified engine, a single core and a single query language. So that means that you're not querying different data stores, or you're not using different query languages for each sort of query that you want to do. You can nest a document lookup in a graph traversal and vice versa. You can perform full text federated searches alongside a graph traversal, all while using AQL. And this is, I think what makes ArangoDB so powerful is that you have access to all of these data models, all with a single query language. And I am going to try and keep an eye on chat. I thought I just saw something. I'm going to keep it checked. No, okay. And so this is something from our benchmark. This is actually our NoSQL performance benchmark for 2018. And this graph, what you're looking at is how we stack up against single store databases. So having a multi-model database is only really valuable if you can kind of compete with single store in performance. And we definitely can. So I won't go through all the metrics here, but this is just a look at the various write speeds and performing things like shortest path and neighbors, and then just taking a general look at writes in a cluster as well, as ArangoDB is a scalable multi-model database as well, which is key. As your use case and product itself begins to grow, it's going to be important to be using a product that's going to be able to grow with you. And we definitely can. And so if you'd like to view this, this is another thing available on our website through our blog to get a full idea on what these metrics mean and really how we perform this test. And we're actually also working on an upcoming benchmark as well. As you can see, this is from 2018, so we need a new revised one that really lets us take advantage of a lot of the new features we've added over the years. And as the slide says, the world loves ArangoDB. And as I mentioned, we are a leader in the graph database category for over 2 years now on G2 Crowd. And something that I think we're all kind of personally happy about is that we have the highest rating for support and flexibility on Gartner. And this is beating out these much larger companies like MongoDB and Neo4j. With a company, like I said, we're proud to be above 65 employees, but that is relatively small as far as employees go. So to be able to offer this sort of support and product flexibility is really, really important for us. And then on DB Engines, it's just a ranking engine, ranking website. We are top 10 in all supported data models. Okay, so now for this section, I would like to show a little bit more on some of the data models and some of the features that we offer, just to give a little bit more insight into what exactly it is I'm talking about when I say that we have access to like a document and a document store or like a search engine, what all that really means. So ArangoDB is a NoSQL database. Our documents are structured as JSON-like documents, so you can use JSON syntax, and that's the way our documents will work. Here, this table is a quick comparison between SQL and AQL. We have databases, but we also have a collection, which is somewhat equivalent to a table. We have documents versus rows, attributes versus columns, and so on. The other thing is that we are a graph database. So you can structure your data as those just normal documents, or you can define these edge collections, which is what's showing here with this ax_n. And we have system attributes that define where an edge collection starts and goes, but you can traverse these edges in either directions. That's all dependent on the query itself. So having this flexible query language allows you to define this sorts of criteria that says which direction you're concerned with, or if you're not concerned with any direction, you can just specify that you want to traverse in all directions. So there's a lot more there to the graphs, but this is actually also a screenshot from our built-in graph viewer. So you can visualize your data as a graph right in the built-in web viewer that comes with ArangoDB. Again, kind of going back to our query language, this is a quick comparison between SQL, AQL, as far as what that syntax might look like. But the goals of AQL included having a common query language for all the data models. So that was the #1 reason we needed to have a query language, was that since we support multiple data models, we need a query language that also does that. The aim was to be human readable. I feel that, depending on the programming language you're coming from, AQL is going to feel very natural, and it is sort of SQL-like. So it's pretty easy to pick up if you're already familiar with SQL. Again, the key goal is being able to use this across all data models, and this shouldn't change depending on the driver you're using. Just a quick look as well at the graph syntax. So while you can perform this document style lookup where you're looking at individual documents and collections, you could even nest this afterwards and use that document as your starting vertex to then traverse the graph. There's going to be a lot more than I can cover in this workshop, but just wanted to give a quick look at what that syntax might look like. We also have a built-in microservices framework we call Fox, and this allows you to write synchronous JavaScript microservices. This is actually executed on the coordinator in the V8 runtime. So this is access as basically as close as you can get to your data with the microservices. You could use this as almost like a backend API for your web application. There are a number of features there, definitely worth looking into. But this is something that can be fairly powerful as it has such close access to the data. It can be very, very performant and gives you access to JavaScript and Node. And Arango Search. So Arango Search is our built-in full-text search engine. This allows for federated full-text searches as well as ranking. And with our analyzer support, this allows for things such as like stemming and in-gram matching, along with fuzzy search with the form of a suite of Levenstein matching functions. And the way this works is it allows you to actually, in a way, index multiple collections into a view, we call it. And this view is kind of treated, as far as the AQL queries go, is this kind of treated as a collection in the way that you refer to it. So this allows a couple benefits, meaning that you can basically query multiple collections at once using this view, and then you get access to all the normal AQL filtering and matching functions, along with some additional benefits for ranking based on the context of the search that you're doing. A lot more there available as well. We have a really great write-up on our blog that goes into kind of a deep dive on how we brought over Levenstein functions, as well as just in general how Arango Search works. And again, if you are interested in any of these, we also have interactive tutorials available as Python notebooks that you don't need to be familiar with Python really to run, but they give a great getting started there. And this is an example query of searching our movies database here, looking for some keywords, and then doing a graph traversal with the results that you find. And for example, this v_imdb would be a view that was created by indexing those collections. And again, this is just a look, but this is combining a search query along with a graph query. This is just an idea I wanted to show off of nesting these query types. And finally, we have enterprise-grade security. As I mentioned, we do have an enterprise edition. This is also what comes with our Oasis product. All versions of ArangoDB running on Oasis are the full enterprise edition. And these are really important for companies that are running at scale and have elevated security concerns, such as TLS and integrating LDAP and other integrated user controls. There's going to be a lot to cover there. And if you are interested, of course, feel free to reach out to myself, or we have a lot of information there available on our site. And as I've mentioned a few times, ArangoDB Oasis is our fully managed cloud product. This comes with automated deployments, monitoring, and backup policies, and still is running a full 2-week trial. So if you'd like a good way to get started for free with Arango, definitely have a look at ArangoDB Oasis at cloud.arangodb.com. I guess a very important thing to note is that our cloud offering also supports all the major cloud providers. That's AWS, Google, and Azure. And finally, switching to really kind of just touch on this Arango ML idea. And this is our suite of tools that we are trying to provide to developers to make it easier and more beneficial to work with machine learning and ArangoDB. And GraphML is this idea of being able to run machine learning along graphs. And we have some people that sort of support us in this idea, such as this quote here from James Fowler, talking about making better predictions, utilizing relationships within the data better than you can from just the data alone. And this is really just this idea of graphs in general, and now being improved with running machine learning as well. And so this is our, as I mentioned, the Arango ML, and this is kind of how we see ourselves fitting into this future of machine learning and graph analytics. We have data ingestion support for things like Apache Spark and Spring data loaders, and as well as with these custom Pregel algorithms. This is still an experimental feature, but we do have a number of built-in Pregel algorithms as well, such as PageRank and community detection. And the analytics, ML, and NLP use cases will benefit from these. We have a number of embeddings notebooks showing how you can use embeddings in ArangoDB, as well as extensions and integrations, such as with NVIDIA Triton, NetworkX, and this DGL adapter, among others available through our website as well. And I will kind of skip past this, as we've already brought up Pregel a few times. But again, if you are interested in Pregel, we do have built-in Pregel algorithms, as well as a custom Pregel feature we are working on. And I will go ahead and pass it over to Sachin from there. Otherwise, if there's any questions, feel free to go ahead and ask them now. And also, actually, this is probably a good spot to mention for anyone that has joined. If you have not already, I'll go ahead and paste in the workshop repo. Definitely download that repository if you plan to follow along in the hands-on portion. And also, there is a specific part for downloading a Docker image that you'll want to go ahead and get started as well. All right, Sachin?
Yep. Just. So thank you, Chris, for a very good introduction to Arango database. Now let's shift our gears towards the introduction of NVIDIA's Triton Inference Server. So starting with the important question of why do we need NVIDIA's Triton Inference Server? So NVIDIA's Triton Inference Server is basically an open source inference serving software that simplifies inference serving for an organization by addressing multiple complexities. So Triton basically provides a single standardized inference platform which can support running inferences on multiple framework models on both CPUs and GPUs, and in different deployment environments, such as it could be data center, cloud, embedded devices, and even the virtualized environments. So the one thing which attracted me the most about the Triton server is its capability to host or deploy trained machine learning models from all the major frameworks like TensorFlow, PyTorch, TensorRT, ONNX, Caffe, or even if you have some kind of your custom frameworks, so it supports that as well. So in addition to this, deployment of the models could take place in any of your favorite cloud provider, for example, AWS, GCP, or Azure ML, or even you can also deploy this server locally on your GPU or CPU, depending upon the backend or the want of like infrastructure you need. So therefore, like it provides AI researchers and data scientists the freedom to choose the right framework for their right projects. It's also a very high performance inference server, as Triton runs models concurrently on GPUs to maximize its utilization. So it supports a CPU-based inferencing as well as and the GPU is sure. And it also offers advanced features like ensemble and streaming inference, which helps developers bring models to production rapidly. This Triton server, if you see, is available as a Docker container. Therefore, Triton integrates with the Kubernetes for orchestration and scaling and is a part of Kubeflow. It exports Prometheus metrics for monitoring, and it could also be used with the other cloud AI platforms like Azure ML or Google Cloud AI platform. So therefore, you can say that it helps IT or DevOps or even MLOps engineers to streamline model deployment in production. The next reason for choosing this server is its dynamic scalability. So it supports the standard HTTP or gRPC interface to connect with other applications like load balancers. So, and it can easily scale to any number of servers to handle the increasing inference loads for any model. So Triton can serve tens or hundreds of models through the model control API. So this is how a Triton inference server architecture looks like, with its various connected components and functionalities which it supports. So we start with, if you see on the right-hand side, we start with creating an AI model repository in which we can place our deep learning models with their respective configuration files. The configuration files of a model helps the Triton server to know number of things. For example, the framework backends of a model, like if it is PyTorch backend or TensorFlow or even some custom backend, permissible shapes of the input and output, batch size supported, even also the model versioning, to mention a few of the these attributes. Afterwards, we load this AI model repository on the Triton server in order to start serving these models on a single GPU or on multiple GPUs. Apart from running the server on the GPU, we can also run it on the CPU. So it basically depends upon the backend. So once the Triton server is started, we can start sending the inference request for our input data. So we can write the so from these inference requests, we can receive back the predictions or embeddings depending upon the use case. So if you see here, on the left-hand side, these inference queries can be written in client applications using Python or C++ library, which interacts with these models hosted on the Triton server. Yep, and it supports different type of inference queries through advanced batching and scheduling algorithms. It also does support live model updates and run models both on CPUs and GPUs. Yeah, apart from that, Triton is also designed to increase inference performance by maximizing hardware utilization through concurrent model execution and dynamic batching. So from here, we will see some of the main features of the Triton Inference Server. So the first one is what kind of models it supports. So as I have already told you that the Triton can load models from local storage or cloud platforms. As models are retrained with the new data, developers can easily make updates without restarting the inference server or disrupting the application. So these are the list of the models it supports. For example, PyTorch, it's JIT traced version, then TensorFlow, Caffe model, and ONNX or TensorRT. Yep, and the next feature is it's support the multi-GPU, which automatically creates an instance of each model on each GPU to increase its utilization, so without writing any extra code. It also supports this real-time inferencing, batch inferencing to maximize GPU or CPU utilization, and streaming inferences with built-in support. Example, audio streaming. So, yep, and so the batching here, I mean, why it's important. So batching here helps for the better utilization of GPU. User-defined batch sizes is required. So in dynamic batching, the Triton implements multiple scheduling and batching algorithms that combine individual inference requests together to improve the inference throughput. Yeah, and the other feature it provides is the ensemble model support. So it also supports model ensemble for use cases that require multiple models to perform end-to-end inferences, such as for autonomous vehicles or conversational AIs, where we get this continuous request for the inference. So the next feature it has is the concurrent model execution support. So multiple models or multiple instances of the same model can run on GPU or CPU simultaneously. The next feature is the model repositories, that where actually we can place our model repository. So it could be placed on your local file system or on the Google Cloud Storage or MS Azure or even Amazon S3. So one thing about Amazon S3 is that these are feature plays actually very important role of placing these model repositories into any of your favorite cloud services. Because I mean, if we want to deploy the Triton server on the cloud and and then we can make inference requests via the most popular, let's say the Lambda functions in case of if you are using this AWS cloud services. The other feature it provides is the metric support. So the Triton server also provides metric support in Prometheus data format, which helps us to evaluate server throughput and latency. And the next feature is the model control API. So with the help of this feature, we can explicitly load or unload models in and out of the Triton. The other cool thing about the Triton server is that like it provides you about 3 control modes to somehow manipulate your model. So which are like none, poll, or explicit. For example, like in the polling mode, server attempts to load all the models at runtime, and changes made to the model repo will be detected, and then the server will attempt to load and unload model based on changes. So here you don't need to first restart the server whenever the new models comes in. So with the help of the polling, it does these things automatically for you. So the last feature which we will see here is the model versioning. So for instances, if you have a, so you can actually, with the help of this feature, you can serve or deploy any of the selected version. For instance, if you have, let's say, developed two models from the same data set, but with the different hyperparameters, and you want to choose the one model, then this versioning can help you. Or you have trained same two models, but on different data sets. So this model versioning feature plays quite an important role in this scenario. So this is the typical model configuration file for the models, which you place in the model repository. So this configuration files contains the detail of permissible inputs and output types, favorable batch sizes for your model, versioning platform, what kind of platform you use, that the model is being using. Since the server doesn't know the details about these configurations, therefore we write them into a separate config file with every model. So if you see here on the right-hand side, so this is an example of model configuration file from a transformer library. So we start with writing the name of the model and then the platform which the model is being trained on. So here it's the PyTorch, and then what is the maximum batch size. And then here, this first attribute is of input. So since this transformer accepts two inputs, so we just tell the server that, okay, we need these two inputs to make an inference request. And these are the dimensions. So these are like the dimensions of the inputs, of the two inputs. The first will be 1,256, and the second input also requires these dimensions. If these dimensions criteria doesn't met, then it will give you the error. And this is the output. What will be the expected output from the model? So when you pass an inference, or you pass this input to a model, so the output which you can expect is of this 1,3 dimensions. So yeah, this is the model configuration file. Yes, so now about today's agenda, about the hands-on session. So what we are planning to do in the hands-on. So first, what we will do is that we will set up Triton server locally on our machine. Then we deploy our first trained model. And then we explore the image client script, which basically interacts with the model, image models being served on the Triton. Then we will deploy almost with the help of, we will write a script with the help of which we can deploy almost any Hugging Face transformer model on Triton server with an application to ZeroShot text classification. Once the model is being created and deployed on the Triton server, we can write a Python client-side script to send the inputs and get back the predictions. So at the end, we will study a use case for movie recommendation, where we will see that how these both technologies, NVIDIA's Triton Inference Server and Rango database, complement each other. So yeah, this is kind of the flow which we are going to use for our case study. So the data set which we are going to use is the IMDb data set. So here, these numbers basically shows you the timeline of the events. So first, we create a Triton acceptable model. Then we place it in the model repository, and then we deploy it on the Triton server. So now the model is being served there. Afterwards, what we do is that we write a front-end client application which basically interacts with the Triton server. So what this script will do is that it will read the movie descriptions from IMDb dataset And once it reads those descriptions, it will pass those descriptions as an input request to get back the movie embeddings for all the descriptions. So once we have the movie embeddings for the movie descriptions, we will store it in Arango database. So now, right now, like we have the movie embeddings stored like in our database. And afterwards, what we can do is that we perform a similarity search. For example, let's say like the new movie comes in with the Star Wars description. So it has Star Wars description, and what I need is that I need the movies which are similar to the Star Wars. Okay, so it means that these movies, the movies which I get back should be some kind of having a genre where we see some space adventures, or it's kind of a science fiction movie. So we get the description of Star Wars movie. We hit the description to the Triton server. We get back the embeddings for the Star Wars movies, and then we perform the similarity search between all the movie embeddings which are there in the Arango database and between our query movie. And so we do this with the help of AQL query language, and it will return us the top 10 similar movies in comparison to our query movie. So this is the general flow which we will follow in this hands-on session. Okay. So now that it was about the presentation, and now let's start the hands-on, and I hope you guys have already downloaded the required packages. So let's start. Okay, so we will start with, so actually what I have decided that we will see the two applications. The first one will be the ZeroShot text classification application, and the second one will be the movie recommendation application. So let's start with the first one. So what we need to do is here that the first step is that if you see the first step here, so the first step is to create a transformer, a Triton acceptable model. So what is meant by this is that we need to perform a trace or convert this PyTorch transformer model into a Triton acceptable model. So what we do is that we will load this necessary libraries, and the model which we are going to use for this session is sentence BERT. And yep, so here we are gonna load and convert the Hugging Face model. So let's do that. Okay, so we did that. So first let's understand like what's actually this tracing of PyTorch models mean. So if you see here, so what it says that the conversion, so we need to perform the conversion using its JIT traced version. So according to the PyTorch documentation, Torch script is a way to create serializable and optimizable models from the PyTorch code. So what actually we are doing here is, so this line is important. Let's do it. Yeah, so what we are doing here is that we are exporting a model which basically requires a dummy inputs and standard length to execute the model forward pass. So what we are going to do is that we will create a dummy input, and then we will perform the model forward pass with this dummy input. So during the model's forward pass with the dummy inputs, what PyTorch does is that it keeps the track of different operations on each tensor and records these operations to create the trace of the model. Okay, so since this created trace is relative to the dummy input dimensions, therefore the model inputs in the future will be constrained by the dimensions of the dummy input and will not work for the other sequence lengths or batch size. So what does it mean? Let's see this. Let's see this as an example. So here we have created our dummy inputs. I'm going to run this cell, and yeah. So if you see here, what's happening is that we are going to create a trace with this dimensions 4,256. So we're going to use the two inputs. The first are the input IDs, which we get basically after performing the tokenization. And the second inputs is the attention mask. Okay, so in future, if we want to perform the inference on this model, then it will only work on these inputs. So if here you try to do it like something, let's say 3,256 or 2,256, it will not work, because the trace or the which is being done is with this dimensions. So all the tensors operations when we perform the trace are recorded according to this input dimension. Yeah, so it is therefore recommended to trace the model with the largest dummy input dimension that you can think can be fed to the model in the future. So I thought like, okay, 256 would be a good criteria. So it's the length of the string. So 256, I mean, it's for this workshop, 256 is okay. So I started with creating a trace with this length. Okay, so understanding this part is very important. Afterwards, what we have is, so here I have written this class, which basically performs the forward pass on this dummy input. So let's run this. And okay, so we don't need this one. Okay, so here we are, what we are doing is in this cell is we are creating an object for this class, setting it to setting the model to evaluation mode, and then performing the trace here where we need to pass this object and then the input IDs and attention mask as of from here actually. And yes, and then what it will do is that it will save this traced model in your current working directory. So let's wait for a couple of seconds. Maybe I can. Yes, okay, so the trace is being done. So now the model will be saved in the current working directory. So now what we can do is that we can copy this model into the model repository, in which we will place all our model, and afterwards, like we will give we will tell the Triton server, okay, here all our models are stored. And if we do this, and yeah, it will copy it in this repository. So maybe I can show you this quickly because I have already done these steps. Let's show. Okay, so here actually I have created my model repository, if you see here, and then what you will see that like this is basically the the model which you are trying to build. So I have named it as DeepSet. And then, so this is here our folder. So actually these are like the further steps. So once you have this model, what we need to do is that we need to write the model configuration file of it. So as I have told you that like Triton Server does not know that what kind of inputs and outputs are expected. So here we will write the configuration file. So here, if you see here, so this is the name of the my model, which should be the same name as of the folder which we will create for our model repository. And then the platform is which we have used is the PyTorch libtorch. And yeah, so as I have told you that these are the inputs. Actually this model requires two inputs. The first one is the input IDs and the second one is the attention mask. So this should be, so this is kind of the strict rule. If you pass the inputs, it should have this dimensions. Both of the inputs should have 4,256 dimension, and the output should be of this dimension 4,256 and 768. So 768 basically here it represents it's the word representation of this whole sentence. So here 256 basically 4,256 basically means that, so here we are having this one string which is represented as 256 256 input IDs or 256 tokens, you say. And then we have this is the first one. This second is the business label, and then the third is art and culture, and then the fourth one is the politics. So here each of one is represented as 256 long characters. And yep, so then what we need to do is that we need to create this model configuration file. So I mean, if you have also already prepared that, or you can also prepare that. For example, if you go to the inception graph of your inception graph folder of your repository, then you can see that this file is already there. So what you can do is that you can copy paste. You can copy paste this configuration, and then you can create this new config file. And so it will be like, and then you need to place it. First, you need to create this DeepSet folder, which I guess like will be created over here. Yes, and then you need to create this config file. You need this config file actually. You need to place it over here, and then you need to place this your traced model over here. So this is actually the basic hierarchy which we need to follow. So here also you can see this hierarchy that we have this model repository where we store all our models. So yeah, so this is actually how it looks like. So we have this our model repository where we will store all our models. Yes, so once you have created your model repository with this DeepSet model, what you can do is that you can run this server, Triton server. So let me show you. So I guess like I'm already running it, and first I will stop it, and then I will show you like how to. So this command actually it's already there in the GitHub repo. So this will run the Triton server. So these are the two ports available. So, but actually there are three. So these three ports provide the three different services. The first one provides the HTTP request, and then the second one is for the gRPC, and then the third one is also there, which we'll use for Prometheus for the metric support. And then, so minus V flag. So minus V flag basically tells the Triton server where actually my model repository is there. So you can see that my model repository is placed over here. So we provide this path, and then we map this path to this models variable. Afterwards, what we do is that, so this is like the basic syntax. Afterwards, we provide this variable to this flag of model repository. So if I run this, and yeah, you can see. So you can see here that right now my Triton server has started, and currently it's hosting two models. The first one is the deep set, which we have created right now. And the second one is the inception graph. So the first one is the PyTorch based model, and the second one is the TensorFlow model. So this is what I'm saying you about that this about the importance of the Triton server, that it can host deep learning models from multiple frameworks. Like, so you can see here, the first one is from the PyTorch, and the second one is the TensorFlow model. And we can make inference requests to any of these models. So let's see one example here with the help of this application. So let's see this ZeroShot text classification. So actually, what is ZeroShot text classification? I have already explained here in very short. It's a very short description, but I guess like it will be suffice for the need of this workshop. So basically, as you see, is the ZeroShot learning is the ability to detect the classes that the model has never seen during the training. So here in this block, so in this post, I'm using the latent embedding approach, in which what we'll do is that we will find the latent embeddings of the given input sequences and hypotheses, which are nothing but the labels against which we want to classify. And what we do is that we will embed both of these sequences into the same space of the model, and then we will find the distance between these two embeddings in the same space. So actually, what's the purpose of this model is that deep sentence. So if you see here, it basically gives back you the sentence embeddings of the given inputs. So once we have the embeddings, we can find the distance between those embeddings in the same space of the model, since we pass these embeddings through the same model. So once we have the embeddings, we can perform this similarity or some kind of distance between them. So let's see this. So this is client-side script. Here, what we are going to do is that we will import the necessary libraries which are required to interact, with the Triton server, and then again we'll load the tokenizer. So let's say we actually have some test sentences. So let's say we have this first sentence where we have this, who are you voting for 2021? And the second sentence is, Jupiter's biggest moon started as a tiny grains of oil. And similarly, we have the third sentence. And then what we can do is that we can add the labels. So let's say we are right now restricted towards only these three labels. And then the input sentences should belong to any one of these three labels. So yeah, we have created these test sentences. So this script basically, this function basically receives sentences as an input and preprocess it. And then this hit the server with this preprocessed inputs and then get back the embedding. So from the server. So once we get back the embedding. So here we receive the embeddings back. So we get the input here as a sentence, and then we perform some pre-processing, like we perform tokenizing of the input sentence, and then we have this attention mask, which is like input IDs and attention mark. So these are the two inputs which we need. So as you can see here, that the shape is 4,256, and yeah, and here we get the embeddings, and then once we have the embeddings, we can get the sentence representation from these embeddings by taking the mean over the first dimension. So the dimension here is basically 4,256, 768. So we take the mean over the first dimension. And yes, so once we have this sentence representation and the label representation, so here we are going to have the one sentence representation, because we hit the server with one sentence at a time, and we try to classify against the three labels. And yeah, we will find the embeddings individually for this input sentence and individually for these three labels. So let's run this script function, and so let's now perform the inference request. Yeah, one more important thing about the similarity function, which is quite important, and I guess like I forgot. So the similarity function which I have used. So once we have the embeddings of the sentence and all the labels, we perform the cosine distance between those sentence representation and all the label representations. So what does this cosine does is that it retrieves the closest label to the input sentence based on its embedding. So actually so this is the typical formula of cosine distance, where we are having this the vector, two input vectors, and then we are normalizing these vectors divided by the normalization of these vectors. So once we calculate the cosine similarities, we can then sort the labels according to the highest similarity. So I have run this cell. So what we can see here is that the input sentence was this one. Who are you voting for? 2021. And then what it has found out that this sentence is very close to the label politics with this much similarity, or with this much cosine similarity, 23%. And the second one is the second closest one is the space and science with this similarity, and the third one is the business. Similarly, if we see the second sentence is Jupiter's biggest moon started as tiny grains of hail. So here also what we see is that the similarity score is 39 with this label. So it means that this given input sentence is very close, which it does. So this sentence is related to the space and science. So that's why it has given this highest similarity. The second one is the business and the politics. And similarly for the third one is this sentence, hi Matt, your payment is 1 week past due. Please let us use the link below to make your payment. So if you see here, so definitely this sentence belongs to this business class or label, so which it has predicted well, or the similarity is good between the input sentence and the label. Yeah, so there's one important note here is that so actually we have used this sentence BERT model, which is it's not that big model, or it's not that that powerful as compared to the other available models like Robota, which can dramatically improves the results for the zero-shot text classification. So I have also written a blog post which will walk through from the same process, but with the more advanced transformer models. Here I haven't used the Robota because it requires a GPU, and I thought that most of the audience would be having the CPUs, and also this model is quite big, and it's kind of like will do no justice to the audience, as what I thought is that like we will do these hands-on session together. So the most of the people who are watching this workshop, they don't have this GPU enabled. But yeah, anyways, so these scores actually increase dramatically if we use the big models. So this is the first application, zero-shot text classification. And yes, and the other application which we are gonna see is this one. We will study this case study where we'll observe that how Triton and Arango database technologies complement each other. So now let's open those notebooks. So again, what we need to do is that we need to create again a trace of the PyTorch model, which we're going to use for our basically for our case study. So here is the trace available. Yeah. Okay, so we'll repeat the same steps: importing the libraries and putting the same model, performing a trace on the dummy input. But this time, what's the difference is that this time we are going to perform the trace with this dimension. So because now what we need is the embeddings of the single sentence only. We actually, if you see here, we are kind of in this in this script, the shape was 4 because of we are performing this batch encoding because we need to perform this zero-shot text classification. So that's why since we need to find the similarity against all these labels, so this remains intact, and we need this, and then we perform the trace with these labels and with this given input sentence. But here we don't need the labels. We just need the given an input sentence. We just need back its embeddings. So yes, again, we follow the same process here. We perform the trace, and yep, so if you see here, we follow we are performing now the trace is being performed with the dummy input. And yes, again, we save this model in this hierarchy. So actually, again, I have already created this this model, and apart from that, like here, it's configuration file. So it's basically remains the same as of the previous model, but only here we name the change. The changes made are like the name of the model, and then there the dimensions. So here the dimensions with which the model is being traced is basically 1,256, and the output dimensions and the expected output from the model is the embeddings, and these are the expected output from the given model when we perform some inference request. So let's see this. So we are at right now at this stage at 1. So we have the model now. What we're going to do is that we are going to now place it over in the model repository. So let's see. So this is the sentence part. So actually, I already have this model created with, if you see here, I've created with its version. So 1 represents here the version number. I have already have the config file, and the model is already there. And what we can do is that we can first, since there's this, since my PC doesn't, it's not that, although it's MacBook Pro, but it's not that powerful to host 2 transformer models at a time. So what I'm going to do is that I'm going to delete this, and then I'm going to, so we have this, copy here, and then paste it over here. Whoa, so we have our model. Now what we are going to do is then again run this. First we need to stop this server, and then again, since we now have a new model, then again we will run this Triton server with the newly added model. So that is the thing about the polling. So it provides basically the polling feature. If we enable that feature, so what it does is that, so you don't need to repeat this process of stopping the Triton server and then starting it again whenever there's new model added. So it automatically detects the changes you have made after some regular intervals of time, and then it does this process for you. So yeah, this feature is quite powerful, and would be quite powerful if you have deployed your models in production. So okay, so these are the so we can see that that the model is now being hosted on the Triton server. So now what we can do is that we can start making an inference request over it. So now the model is running. This step is completed perfectly. So now what we need to do is that we need to build this front-end client application which can interact with the sentence bird model being hosted over here. So as we go back here, so we already have created this movie recommendation application. So yeah, so this notebook basically talks about word embeddings and what are word embeddings, or what are sentence embeddings, and what is the importance of attention mechanism, what is the importance of transformer models, like how they have beaten the previously used sliding window approaches. So yeah, I'm thinking since the aim of this workshop is not to go into deeper into this explaining what transformer models are, what are their advantages, but rather about the next steps. Like once you have the models, then how to deploy them and how to make inference requests and what to do afterwards. Like what? So I have seen that like most of the people can create the models, but the next things which comes into the picture when you are working in industry is like what to do afterwards. So this is what like this workshop is about, deploying the models. Yeah, I guess like I have already given you a pretty good introduction about this transformer models and embeddings. So I'll just give you the brief overview of what embeddings are. So they are just the numerical representation of the text consisting of ordered sequence number called the vectors. So here the idea is that if we have the sentences, let's say if we have the two sentences, and then we get the embeddings of those sentences from the trained models, then if we map those vectors to some two-dimensional or three-dimensional space, then the idea is that these, for example, these here, you can see these vectors representation of a word or a sentence. If they are similar, they should be very close in this Euclidean space. So if if the two sentences are very dissimilar, then they should lie very far away in the Euclidean space. So this is the main purpose of embeddings. So the similar sentences should lie closely in the embedding space, and the dissimilar sentences should lie far away in the embedding space. Yes, so to start with, what we need to do is that first we need to create a setup here. So let's create the setup. So since I have already installed these libraries, torch, transformers, I don't need this. Maybe I need Pyrango and Python Arango. Oh, it's still using the objects. Okay, so we are done with this and then import these libraries. So again, initializing the tokenizer. Again, since we are using this, same model here, we're going to use this same tokenizer from that model. And so let's try with some random input sentence and extract it sentence embeddings from the sentence BERT model, which is deployed on the Triton server. So we have this. Let's say this is the sentence example. Who are you voting for 2021? And so this is again the client side script to interact with the Triton server. So again, it's receive the input sentence. Then here you see here the model name, it hits this model. So this service, the Triton server, is basically running at this port. And then the version of the model we are using is the first. And apart from them, this is the same. We perform the tokenization of the input sentence. And yeah, converting the inputs into Triton HTTP client. Yeah, let me see. So here, Okay, so yeah, we can run it. So since we have run this, and let's see. Whoa. So we have got the embeddings for this given input sentence. So as you can see here, this is the word. So this basically at this point of time we get the word embeddings where we get the embeddings for all the words in the sentence, but we can convert it into the sentence representation by taking the mean over the first dimension, and here we get this sentence representation of this given sentence, or the embeddings of this given input sentence. Then the test was successful. Now we will perform some Arango database setup, and let's start with creating a temporary database. So basically what this does, this cell does is that it connects you to the temporary database, and yeah, and here it provides you some temporary credentials which remains for some time. So you can also click this URL and have an interactive ArangoDB web user interface where you can see, like, I mean, if you are performing some operations on the notebook, and you can see through this user interface, like what's happening, like how the things are getting stored and what are how the manipulations are being done. So you just need to enter the username, the password here. And yes, we can select this database. Okay, so this is how our user interface looks like. It's the most important feature of Arango database, collections. Right now it's empty, but soon it will not remain empty. So about the dataset, we are going to use this IMDb example dataset. So this dataset basically contains the information about various movies, actors, directors as a graph. For example, yeah, this graph you can see here. Basically, it represents the connections between all these entities inside the IMDb dataset in a very visualized manner in a graph format. So yep, so this is basically how the data set looks like with the nodes. Then you have these relationships, basically X in, for example, some actor X in. So this is X in basically relationship, which shows you, okay, there's some actor X who acts in some movie Y. Like this is how this graph is being created. And then what we are going to do is that we will perform this Arango restore operation, and what it will do is that, so it will automatically add this data set, IMDb data set into this created database. So yeah. And yeah, we have to wait for some time. So once this data set, IMDb, is restored to this temporary database, we can see this, okay, it's there already. We can see the different types of collections here. Okay, so it's done here. So now you can see that now it has that Arango restore command has populated our temporary created database with all these collections. The important collections for this workshop is the IMDb vertices, which includes the description about the movies. Yep. So for example, this description. So if you open this document, then you can see this description is provided. So what we are going to do next is that if we see this diagram from our this client application, we are going to fetch the movie descriptions from all of these documents. And then what we are going to do is that once we have this descriptions, we are going to get the embeddings for these descriptions from the Triton server, basically from the sentence BERT model. And once we have these movie embeddings for all the descriptions inside the IMDb vertices collections, we can store these embeddings, movie embeddings inside the Arango database. So let's see this. Where we okay, so it says that we'll start by retrieving all the movies that we want to produce the embeddings. So yes, so this we do this by using this our AQL query language, where what we do is that we will go through all the documents. So these are called the documents here. So we will go through all the documents, then we will filter. So the so you see here. Sorry. You see here, these are all the attributes inside the document, like description attribute, genres, image URLs, and all. So what we are going to do is that we are going to fetch the description attribute here, filter the documents from this attribute, and yep, and then storing these descriptions into this variable. So once we have it, and then we can store these movie descriptions into a data frame. So let's see this. Yep. So if we see this data frame now, this data frame contains the IDs of all the movie descriptions of all the movies or IMDb vertices and their corresponding descriptions. So we are having like 9,500 vertices in our collection. And yes, we don't need this. So now the next step is that we will iterate over this descriptions inside the data frame, and then we are going to produce the sentence embeddings from it. So this is the script for it. We are going to iterate over the movie data frame, and then we are going to use this description column, which contains all the description. And then once we receive these descriptions one by one, what we're going to do is that we are going to run the inference on this description. So let's say we start with this first one, description Lawrence, he counts to it. As soon as we receive it from here, we call this function and run inference. And here you can see that this function will give back the sentence representation. So let's start and run this script. So as soon as we receive the sentence representations, we can store it in this list, all embeddings, and afterwards, like, we can concatenate all the embeddings, all the movie embeddings, and then we can here what we can do is that we can create one more column of sentence M, which will contain all the all those vectors representation. Okay. So you can see here we are receiving the embeddings now, but the problem with running these on CPU is that it's gonna take a hell of time. So what I'm gonna do here is now, so I have already ran this this script, and I have already stored these movie embeddings for all the movie descriptions inside a dump. And what we can right now do is that either we can restore this database. We can perform the restore operation on database, which will dump the already created movie embeddings here, or we can see we can perform this similarity search with the with this script here. Okay, so let's see here what we can do. Okay, let's perform this dump here. So what we are gonna need is that, so when you download this let's see. So actually, when you clone this repo, so we have already created this dump inside this repo. So this is the repo, and so we have already created this dump. So what we can do is that we can use this dump, which already contains all the movie descriptions with all their corresponding embeddings. So we can restore our database with this dump. Then what I need to do is that, let's see, we need to run this command again. Just thinking if I have this. So we need to, I need to paste the path to this dump. Let's get the path. Okay, so so here is There's my.
You'll probably want to drop the collection since you've already restored that.
Yeah, exactly. I'm gonna do it next. So. Or what we can do is that we can create this new database correction. Okay, we can request for the new credentials. Then maybe we can, since
Are you trying to drop the collection?
yeah.
Okay, click into it and then go to settings, click into the collection. No, into the, actually click on the collection, the IMDb edges. Settings. And the left side, like kind of, yeah, there you go. And then delete.
Okay. Okay, so we don't need this as well. So now what we can do is that we can again run this Rango restore with the dump, which already contains these movie embeddings and the movie descriptions as well. So let's see. Let's wait for a couple of seconds. Taking a while. Okay, let's see what's happening over here. Oh, that's a good sign. At least we are receiving sometimes. Oh, it's finally done. So now you can see that we have all our connections with the movie embeddings. So let's see if we can find some. Here it is. So now initially we will just we just have these descriptions. Now if you see here, this document also contains the respective movie embeddings for this description. So now we have the description, we have its corresponding embedding. So now let's move to find the similar movies given a query movie. So where are we? So yeah, okay. So right now we have already stored the movie embeddings in our database. Now what we're going to do is follow this step 7, where we pick some random movie embeddings and then try to find the similar movies according to cosine similarity. Where we perform the similarity between all the movies, which are all the movie embeddings which are there in the database, and this input are our query movie embeddings. So yeah, and then we do this process using the AQL query language. And let's just do this. So yep, so let's say I have picked this movie, which is basically the Undefeated, and the description says, okay, it's a Civil War movie where this colonel was there, and then this Union Army of Mexico trade Oasis, its opponent, and blah blah blah. Let's see if we can find the similar movies according to this query movie. Well, how we are going to do is that we are again going to perform the cosine similarity between this movie query and all the embeddings of the other available movies. So we are going to do this with the help of our EQL query language. So let's actually run this and see what's happening. Oh, it's there. Whoa! So we have it. So the first movie which it has recommended us according to this movie, it's the movie itself, giving the similarity score of 1, but we are gonna not see this one, but the other similar movies to this Undefeated movie. So the first one is the Time for Killing, which is having the cosine similarity score of 69%. So let's see on the internet what actually is the description of this movie. If we open this and see this movie description, and we see that, okay, so this is Confederate soldiers during the Civil War escape from a prison and go towards the Mexican border with the Union troops chasing them. Both teams are unaware of the war ending and peace being declared. Okay, so which is exactly or quite the same to our query movies, to our query movies. So this, you see that it's also about the Civil War, where we are having this army soldiers, and it's also the place of this somehow war or the events being taken place in the Mexico, where also we have this Civil War, and we have this Union troops or some army person, and also here the events are happening in Mexico, and yeah, so it looks that it actually works. So next time, if you have watched some movie and you don't know and if you have already liked that movie and you don't know what other movies you want to watch, then maybe you can run this script in your home and then you can find it out. So this was all about running this use case, and the thing now, I guess I'm thinking what I'm left with. Okay, so I'm left with this trained model. So we haven't talked about this TensorFlow model. So where is this model hiding? Okay, so here it is. So this is basically inception net model, which comes with this Triton Inference Server repo. So when you download this Triton Server repo from their official website, so this is the by default model. So I'm not going to go into the details of this client script, image client script, which also comes when you are cloning this official Triton Server repo. So maybe, but I can show you the script and then I can perform one inference request on our example image to see what basically it predicts, or it's basically a classification, image classification script. But let me first open this. There it is. So this image client script basically is from the NVIDIA. So this, as I told you, this comes with the repo itself. When you clone it, and you also get this inception net model with its required directory structure for the Triton server, and also with the configuration file. So let me see. So first, let's see this script briefly. So this is the script, and the most important part, which I can show you, is about the pre-processing of the script. So once we receive the input image, it performs the it performs this pre-processing operation. For example, to meet the size of the input, the type, and the format, that whether it's these formats, whether the channels comes first or the channels comes at last, and all other things. So basically it checks a lot of criteria. So here it also perform the resizing. So this inception net model requires the size of your input image to be 299 height and width, and then with 3 channels. And if you don't provide that size, it typically does for you. And then it also performs the scaling operation on the input image. I mean, if you're using this inception net model, then this is the scaling criteria it uses. If you're using VGG, so this is the scaling criteria it uses. So yeah, and then this is the post process, which gives back you the classification results. So I guess these are the 2 main important functions we have. The other ones are basically basically analyze the metadata with the model and connecting. So for example, this argument basically connects you with the default local host where your server is running, and here about which protocols you want to use, gRPC or HTTP. So I guess, yeah, these, I guess, are the important one. So let's just try some example using this image client application. So let me see where I have terminal. Okay, so we can use this. To start, let's see. Just looking for a good image. So okay. So we run this file, and so this is basically the client side script for the Triton Inference Server to interact with the image models which are hosted on the Triton server. So we run this script, and so this flag basically tells you about like it gives you basically the top 3 classification scores or top 4 classification. So you can change it over here if you change it with 4. So it will give you the top 4 classification scores. And then -m flag basically tells you about the model on which you want to make an inference. And then -s is for the scaling flag, which I have shown you that since this model is the inception model and we want to perform the same scaling on the input image. So we have, oh, no, we are in the wrong directory, so need to change the directory. And let's say we perform some classification on a car image. So let's see what it gives us. Okay, I have to activate my environment where all Triton client libraries are there. So let's activate this. And now if I run, so let's first see this image. Oh. Okay, so here is the image which we are gonna pass through this script, image client script, to our Triton server, which is hosting our inception net model. So the inception net will receive this image and it will classify it. So let's see how it's classified basically. So it classifies that it's a sports car with 81% probability, then it's a beach wagon, and then there's a car wheel. So we can also manipulate this with, I mean, if we want this, let's say the top 4 predictions. So let's see what will happen if we get the top 4. So yeah, the top 4 predictions, if you see, again, we have here now the new one, which is a convertible car, which I think it looks like. So yeah, so this is how we can interact with the basically image models, which is this one, inception net. So this is the TensorFlow 1 model. And yeah, and so this was our hands-on session where we have seen a lot of notebooks starting from creating a Triton acceptable models, from Hugging Face transformer models, and since we cannot place these Hugging Face PyTorch models directly to the Triton server, so therefore we need to perform the trace of the PyTorch models, and then what is the configuration file which we have always need to write when we are creating models for Triton Server. And afterwards, we have also seen this case study of ArangoDB meets Triton Server, where we have seen that like how both of these technologies can complement each other. So one can, Triton Server can be used for performing the inferences on the data stored in the database, and then the Arango database could be used to perform the operations once we have these inference results through their AQL query language, or also through its various graph analytics functionalities which are inbuilt in the AQL. So we can also, so once we have the data stored in the database, we can perform graph traversals using AQL and so on. So that's all about today. And as I told you that, I'm going to also give you the glimpse about our second workshop, which will tentatively happen on September 1st. So here, what you can expect in this workshop is, again, we set up the Triton server local machine, then there will be an introduction to graph machine learning. And like here, we will, once we have the basic foundations of graph machine learning, then we can train our first graph machine learning model, which is none other than the popular inductive representation learning algorithm graph SAGE. We are gonna do this workshop using the PyTorch geometric library, and the dataset which we are gonna use is the Amazon co-purchasing dataset. And so once we have this trained graph machine learning model, we can deploy this model on a Triton server, and then again we can start getting the inference request using the Python client-side script, which basically will interact with the graph machine learning models. So the use case where we can leverage both of these technologies will be Amazon product recommendation. So given product, given us some X product, like what is the higher likely chances that the user will buy the other product together with this given X product. So if you go to do some shopping on Amazon, and if you buy one product, and it could be the chances that you buy some other product together with it. So we will try to address this problem using the graph machine learning algorithms and leveraging the powers of both of these Triton server technology and the Arango database. And that's all. Thank you very much for listening to this workshop. I hope you guys enjoyed it. And if you have any kind of questions, you can ask in the chat. So we can do 5 or 10 minutes chat round. So me and Chris is available right now. So if you have any kind of questions related to the scripts or to Arango database, we can answer your questions.